I feel very, very privileged to be able to host this track in particular, because many of the people we are introducing are people that I've had the pleasure to interact with in the community before. Romain is one of those people. I've been quite obsessed with the discrete event simulations for a part of my life, and that was a time where Romain and I were having occasional asynchronous chats over a variety of different channels, and this is because Romain is actually dealing with discrete event simulations as part of his studies.
Hi, Lorenzo.
Hey, great to see you in person for the first time. Welcome to Crystal 1.0 conference. Very, very excited to have you here. And again,
thank you for the
cheers. And you'll be talking about simulations today. So I'll let you start because we have the right amount of time. So the stage is yours.
Okay, so hi, I'm Romain. I'm currently CTO at Lucky, which is a company based in Corsica. But today I'll be speaking about modeling and simulation and how you can achieve that in Crystal using Quartz, a shard that I developed during my PhD, which is not the shard that was mentioned in a previous talk. It's another, but it seems that there's a name conflict. So I'll give a quick tutorial on how to do discrete event simulation in Crystal. And along the way, I'll also give my personal opinion on why I think Crystal is a great fit for doing science. So my story starts at the University of Corsica, where it's where I started my PhD in modeling and simulation back in 2013. And in science, mainstream languages are still Java, Python, C. But personally, back then, I was using Ruby a lot because how expressive the language is. I was able to focus on the problem domain rather than some details. So I was pretty happy about that. But my work was also related to multi-agent systems. You have an example here on the slides. And those kind of systems involve usually a large amount of components to simulate. And here, Ruby was kind of slow. So the day I found Crystal, I don't remember exactly when, I was really excited because I found what I was missing with Ruby, which is static type checking and performances, obviously. So it didn't take me long to port my code base, and the results showed really promising performances. Since on a particular benchmark, I got a 10x speed up, and I was also able to compete with a similar C++ library, which is in the blue line. Crystal is in the dark red line, and Ruby is here. Yeah, so I was really happy when I found this. So before digging into a practical example, let's focus quickly on why simulation might be useful, not only in academia, but also in industry. Usually, simulation starts with a modeling problem. So you need to capture basically the behavior of a time system as a model that you can later study by simulating it. So it means that time has to be an explicit dimension of the model system. And there are different ways to represent time: continuously, as fixed time steps, and as variable time steps. And Quartz as abstraction to represent the latter two. Today we will focus on the last one, which is discrete events. Also, something I didn't mention is that the nice thing about modeling, it's cost effective, and compared to running real world experiments, simulation can be used, for example, to study the resiliency of a distributed system and so on, but that without actually running it in a cluster. So it's cost effective. It can save you a lot of money. So we'll use a simpler example than the distributed system to showcase Quartz. It's going to be a simple traffic light. But already this is example, it has a nice property since it's timed, it has an autonomous behavior, and it's reactive because we are going to model the fact that, for example, a pedestrian can can interrupt the traffic light if he wants to cross the street. So yeah. So as a framework, the goal of Quartz is to let the modeler focus on the behavior of the system. And so it defines an API for the modeler to define models, and then you can just provide an instance of this model to construct a simulation. As you can see here, the API is quite simple. You just instantiate the model and provide this to the simulation wrapper. And the thing is that the framework will handle the simulation part automatically. So you don't have to think about the simulation loop, jumping between events and so on. This kind of stuff is already provided by the Quartz framework. So you just have to provide the behavior and some parameters, and you're in business. And as a result of the simulation, you will have a simulation trace. So for a traffic light example, we will see, for example, the set of outputs over time. So for example, this bottom chart shows the different colors of the traffic light that, for example, a car driver will perceive over time. And here, the top chart, it's the actual internal behavior of the model. So you can see, for example, that you start in a green state, stay there for 55 seconds, and then you go to the yellow state, stay there 5 seconds, and so on and so on. So what the simulator does is simply jumping between those little dots here, and that's all. So to define such a model, the basic building block in Quartz is called the atomic model. You can define any discrete event behavior based on this simple API. You can see that it holds a state, some input ports, some output ports, and some methods that you can overload, including some state transition methods. So to define our traffic light model, there are basically 5 steps to do. The first step is to define the state. Here we simply have one state variable which represents the different colors. And you can see here that we have a nice way to declare the state. It's a declarative way, and thanks to a DSL that is defined thanks to the crystal macros. The second step then is to associate a duration to each state. So for example, the green state is going to last 55 seconds. And so the simulator will call a specific method, which is the time advance method, to actually know for the current state, what is going to be the duration of this state. And so I put also delays here to showcase that you can have also parameters that you can change for a particular instance of a model before initializing a simulation. The third step is to add transitions from one state to another after it expires. So for example, the green state after 55 seconds, we want to go in the yellow state. So we have to actually make this arrow something which exists in the code. And this happens in an internal transition where we actually assign a new state based on the current state. The fourth step is to define the outputs that are going to be produced when a state expires. So for example, in our example, each time a state expires, we want to send the color that the traffic light is going to have. So at the end of the green state, I want to show the next color, which is the yellow one. And this is what we do here in the output function. We choose a value based on the current state, and we post it on an output port that we declare here, still using a macro. And that's it for the autonomous behavior. We have the time advance function, the internal transition, and outputs. And the simulator will always call time advance, output, and internal transitions in this order to have an autonomous behavior. But for the inputs, we have a dedicated transition function, which is called only when the model is interrupted from this autonomous behavior. For example, if our pedestrian pushes the crossing button, we use this information to shorten the duration of the green light here. We go directly to the two yellow state, which has a duration of 0. So that means that instantly we're going to output the yellow output and then change to the yellow state. And that's it. Now we have autonomous behavior, reactive behavior, and which is ready, but the input behavior is never actually called. If we just simulate the model as is, we are going to have the simulation trace I showed earlier. So it means that we have to have an input events and output input events come from the output of other models. So that means that we can couple some models together to tackle complexity. And that's what we're going to see right now. If, let's say, I define another simple model, which corresponds to the pedestrian, that simply is going to push the button at after 2 minutes and 20 seconds, I'm going to have a slightly different trace from this point in time, because as you can see, the green state is going to last only 20 seconds instead of 60. And you can see that we need an input that comes from another model. So defining simple models and later couple them is a common practice to tackle complexity. And in Quartz, it can be done using coupled models. The basic idea is to add submodels to it, and then you attach the different ports that you define between those submodels, and that's it. And then you provide the coupled model to the simulator, and it will simulate as you expect the simulation. So via composition, you can tackle more complex systems. Already our traffic light could be used to create a really primitive intersection. If you, for example, here we have 4 traffic lights. If we define an initial state that is slightly different for each of them, so for example, 2 at the green state initially, 2 at the red state, you already have some primitive form of intersection that you can study. So I will stop here for the simulation tutorial, and we'll conclude with 2 take-home messages. The first one is that from my experience, Crystal is a great fit for science because it's really expressive, so you can focus on the domain, and it has amazing performances, which is something that is really important when you do number crunching. And something that I didn't mention is that it has a really nice dedicated syntax for C bindings, which is extremely important when you use it for scientific purposes, because a lot of scientific libraries are written in C. And the second message is that simulation is cost effective. So it's useful also in industry. So even if there's a slight learning curve, it may worth the effort to put into, because you can then cheaply understand how a particular system performs. And yeah, you can find more resources in the Quartz wiki, because I took a lot of shortcuts presenting the model. So there's some more information there, and you can read this or reach me directly if you have any questions. So I hope you enjoyed this tutorial, and that's it. Thank you for attending.
Thank you, Romain. I think let's open up for questions. Let's take maybe a couple of minutes while I promote KC to panelists, and I'll ask a question before people start populating the Q&A and the comments. Is there anything you would do differently if you were to rewrite Quartz today?
Yeah, probably, because it was my first Crystal project actually, and so it was written mostly for being able to write some solver parts because part of my work was to define some formalism and test them. So Quartz was basically here to provide a reference implementation for those playrooms. But I think I would use another pattern to write a simulator today. I want to test entity component system like a game engine would be conceived to build a simulator, but didn't have the time yet to play with that.
Thanks, Romain. Romain,
yeah.
Thank you very much for your presentation. Hopefully you'll be hanging around later on the Discord channel, but if not, we know where to find you.
Yeah. Thank you very much.
Again, cheers.
Bye. Cheers.
And